So now this video discusses about what required as the Newton's law of universal gravitation force, where we'll be able to understand what is it all about the Newton's universal gravitation force. We'll be talking about the superposition principle in one dimension as well as the two dimension. But the better understanding of the lesson needs you to understand or to have the full basic knowledge about the vectors, and basically vector resolution into components, and also they actually having the resultant vector and basically direction as well. We should be able to add two or more vectors, the componentry, and that will have the resultant vector as well as the direction. So those are the things that will be actually that you need to understand before you go for this video, because we just have to apply the typical knowledge on the vector resolution as well as the direction and some other concepts to do with the vectors. So keep that in mind. So we should have to understand that we have two types of forces. We have what you call them as conservative forces. So should be conservative forces. So what are conservative forces? Conservative forces, these are the forces that do not change. And these are the forces that remains constant within the particular space or within some particular actually a planet. And the good example is we have the gravitation force. So gravitation force is also part of the conservative force. So should be gravitation force. This is also the part of the conservative force as the main interest of the video. So gravitation force in a given planet remains the same. And now we also have what we call as the electrostatic force. We have what we call as the electrostatic force. And this is also a part of the conservative force. So apart from the conservative forces, we have what we call them as non-conservative forces. These are the forces that do not remain constant, and these forces keeps on changing based on the conditions. They are influenced by different factors, and basically we have the likes of should be the friction force, and this is the force of opposition to the motion of the object, and basically it is affected by the surface area. So the nature of the surface area, the rough the surface, the greater the friction force. Likewise, the smooth the surface, the lower the actual friction force should be that. And I also have what we call as the spring force, and this is the force actually possessed by the spring. So it should be that. And we have several other examples of non-conservative forces that you may think of coming across with. But for the sake of interest, this video won't discuss about what we call as the gravitation force. So you should have understanding that way. So a gravitation force, what is a gravitation force? So a gravitation force, this is the force of a gravity. And this force is said to be the force that is always pointing towards the center of the circle. We call it as the gravitation force. Should be the center of the earth rather than the circle. So this is the force which is said to be the vertically oriented, and it points towards the center of the earth. That's what we get as the gravitation force. And let's say this is a typical earth. Let's say this is the earth. You should have understanding. By the way, earth is round like a ball. So let's say this is a typical earth. And now the gravitation force is said to be pointing vertically down towards the center of the earth. This is what we call as the gravitation force, and it is part of the conservative forces since it remains constant within the given planet. And for the case, we have the gravitation force in the earth, also in the Mars, in whichever the planet that you are familiar with. It remains constant, hence it is part of the conservative force. So should be that. So now, according to the Newton's according to the Isaac Newton, he believed that the free falling objects, let's say this is also the same eighth. The free falling objects, they are said to be falling because of the gravitation force. So whatever the free falling objects is said to be falling under the influence of the gravitation force, and the objects are said to be falling directly, and the objects are said to be falling towards the center of the earth. That is according to the Isaac Newton. He believed that any free falling objects that are said to be falling because of the gravitation force. No any other force is said to be acting on the free falling objects apart from the apart from the force of the gravity. And those objects are said to be falling towards the center of the earth. That should be according to the Isaac Newton. And apart from this, you start to understand that the moon is said to be moving around the earth, and basically in a circular path. Let's say this is should be the earth, and this is the moon rotating along the this is the moon rotating around the earth. Let's say that is the case. And now according to the Isaac Newton, he believed that in all cases this moon is moving around the earth because of the influence of the gravitational force. So the same force that was responsible for the free falling objects, it is the same force responsible for the rotation motion of the moon around the earth. So that is according to the Isaac Newton. So he had two incitations. First incitation is that any free falling object is said to be falling under the influence of the gravitational force, and that is directly pointing towards the center of the earth. And another incitation is that for a case of the moon, so the rotation of the moon, it's because of the same gravitational force. That's according to the Isaac Newton. Now we tend to wonder to say the falling object, the object which is said to be falling, it is vertically, the falling object, it is in a vertically motion. But how about the case of the moon? The moon is said to be moving in a circular path. How should you have the connection between the falling object, which is in a linear path, and on the case of the moon, which is moving in a circular path? You need to understand about this thing. So in all cases, for the object which is moving in a circular path, it possesses three accelerations. And we have what we call as the tangential acceleration, and this is the acceleration which is always tangent to the circle. And I do have what we call as the centripetal acceleration, and now this is the center seeking acceleration, and which is always points towards the center of the circle. And let's say that is the case. That is the centripetal acceleration. We should have it in this way. This is the centripetal acceleration, which is given as ACB. And we have the acceleration associated with a change in the angular velocity, which is the angular acceleration, which is given as that. So now, according to Isaac Newton, this centripetal acceleration, it is the acceleration due to the gravitation force. Hence, it is regarded as the acceleration due to the gravity. And the force responsible for this acceleration is said to be the gravitation force. It's said to be the centripetal force. So should be that. So the same force responsible for the centripetal acceleration on the rotation motion of the moon around the earth, it is the same force responsible for the free falling object towards the center of the earth. As you can see, this acceleration is pointing towards the center of the earth. So those are the two incitations associated with the Newtons, should be associated with the Isaac Newton. So he believed that the motion of the moon, the rotation motion of the moon, as well as the free falling objects, it is due to the influence of the gravitation force. So assuming there is no air resistance in a given space, so should be that. And apart from these two incitations, Isaac Newton believed that in a given universe, in a given space, objects fuse each other. So what was that? objects fuse each other. And what was the point of interest there? According to the Isaac Newton, he believed that if we have, let's say, this is the object 1 and this is the object 2. Let's say that is the case. These two objects fuse each other. And what is that? Because of the force of the gravity. And this force of gravity is always attractive. And now this object feels being attractive towards this. And also this object feels more attractive towards this. This is according to the Isaac Newton. And this analog was actually documented, and he named that as being given as what we call as the Newton's law of the universal gravitation force as the main point of interest in the video. So when I look at how we can have to understand about the Newton's law of the universal gravitation force, and from the fact that the objects in the universe fuse each other and because of the force of the gravity. So how should you have to understand that one? And now according to the Isaac Newton, let's say this is the object and this is the object of mass 1, and let's say this is the object of mass 2. Let's say that is the case, and let's consider the separation distance between the two objects. Let's say the separation distance is given as, let's say, given as r. And now according to the Isaac Newton, these two objects fuse each other, and that's the force of attraction. And there will be a force in which the object 1 will have to experience due to object 2. And there's also a force in which the object 2 will have to experience due to the object 1. If that is the case, we'll have it as the force 1, 2. That is the force on the mass 1 due to mass 2. And this is the force 2, 1. That is the force on 2 due to mass 1. That is. And these forces are the same. And that is F12 is the same as F21, but now they differ in the direction. That will be given as that. And since this one is pointing towards the negative direction. Now, as you can see here, these forces obey the Newton's third law of motion. And the forces are the same, but they differ in a direction. But at the end of the day, how should you have the magnitude of the force of attraction we're talking about between the two masses? By the way, the force is always attractive force. Unlike the electrostatic force that we're going to look up to these other times, electrostatic force is the force of attraction as well as the repulsion. But now for the case of the gravitation force, the force is always attractive. You should have that. So the mass 1 feels more attractive to this. The mass 2 also feels in the same way, being attracted towards this. So you should have that. So the forces are the same, but they differ in the direction. Hence, they obey the Newton's third law of motion in that way. But now our interest is to look at how we should have the magnitude of the force of attraction between the two masses. So how should you have that? And now you should have to understand that the force, which is the gravitation force, is directly proportional to the product of the two masses, and that is inversely proportional to the separation distance square. And let's think of introducing the constant as the equal sign. We have the force being given as G mass 1 times mass 2 divided by the separation distance. So this is what we call as the Newton's the Newton's law of universal gravitation force, which states that the force of attraction between the two masses is directly proportional to the product of the masses and inversely proportional to the square of the separation distance. Hence, Newton's law of the universal gravitation force obeys the inverse square law. So stop that one. And where G is said to be universal gravitation constant, and which is basically given as G being given as 6.67 times 10 to the power should be in negative 11, and that is Newton meter square per kg square. We'll have it as that. And by the way, the masses has to be in kgs, and the separation distance has to be in meters. So keep that in mind. Let's say this is the question. two apples of mass 1, we have the mass 1, which is given as 0.110 kgs, and the mass 2, which is given as should be 0.220 kgs. Sit on a dining room table, treating the apples as point objects. Find the force of gravity between them when their separation distance is a. So we are looking for the gravitation force when the separation distance at first is given as should be 13 point. When the separation distance is given as 13.2 centimeter. Of course, it has to be in meters. So how should you have that? The principle remains the same. The force is given as G m1 times m2 divided by the separation distance. And what is universal gravitation constant, which is given as 6.6, and 7 times 10 to the power negative 11 should be Newton meter square and per kg square. So try to suppose student have all these and have the force in newtons. And by the way, whenever you are plugging this on your calculators, you have to put them in brackets. Whatever the operation you're having, put in brackets, and don't rush to have it once on your calculation. Just have to do it step by step so that you should have the proper calculations, you should have the proper accurate solutions. And also do the same with this one. Now let's see this question. A 6.3 kg, that is the mass 1, we have it as a 6.3 kg. Burying ball, and we have mass 2, which is given as 7.1 kg, like that. And we have their separation distance, which is given as should be 0.85, like that. So what is the force of gravity exerted on each of the balls by the other ball? And by the way, for this, what you have to understand is we need to have the force of gravity. That is a G mass 1 mass 2 divided by the separation distance. As I already put it forward, that the force in which both the experiences is the same, only in that it differs direction. So therefore, just have to understand that each ball will experience the same force that we're going to calculate here. That's how you have to conclude it in that way. So at what separation distance is the force of gravity between the balls equal to? And by the way, this should be given as the power. That is a power negative 9, and this is multiplication there. So now we are being given the force, and we have the masses here. We should have the separation distance in that way. So just have to make R as the subject and have everything out there. And now let's consider this question. In one hand you hold a 0.13 kg apple, that is the mass 1, or called as mass 1, 0.13 kg apple to the apple. In the other hand we have, that is a mass 2, or called as mass 2, which is 0.22 kg. Let's say that is the case. And now the apple and the orange are about, let's say, the separation distance of 0.75 meters. Now what is the magnitude of the force of gravity that the orange exerts on the apple and the apple exerts on the orange? The force will be the same, as I have already put it forward. And now let's consider this kind of equation. Two objects attract each other gravitational with the force of, this is the force of gravity, which is 0.09 newtons. And we have the separation distance, which is 0.25 meters. Let's say that is the case. And now we have the total mass, and which is given as should be 4.00 kgs. So we should have their individual masses. We should have mass 1 as well as mass 2. So how do you think we should have them? Now we have two things to understand here. We have been given the force and the separation distance, and now we have the total mass. So come up with the two equations corresponding to what we have been given. We have the formula for force, which is G, mass 1, mass 2 divided by the separation distance square. We have the force here, and we have the G each value. We have the separation distance here. We have M2 as well as the M1 unknown. That will give us the first equation. On the case of the total mass, what corresponds is that we have the total mass being given as the mass 1 plus mass 2. We have the total mass here. We have M1 as well as the M2 unknown. That is equation 2. We'll solve for this using simultaneous. Now those two equations will be simultaneous equations. From there you'll be able to solve using the substitution method. Try to have that. And now let's extend our discussions by looking at what we call as the superposition principle. Let's say if we have the system of several masses, let's say this is mass 1 and this is mass 2, and let's say this is mass 3. Let's say that is the case. Let's say this is the system A. And let's say we have the system B, which is, let's say this is a mass 1, and let's say this is mass 2, and let's say this is mass 3. Let's consider the system in that way. Now these two actually systems, the first system as well as the second system, those are the systems of masses, as you can see. But now since the masses are in a one dimension, if we look at we look at them as being, we look at the system being, let's say, on a Cartesian plane, you see that the first system is along x-axis. Therefore, this is a one-dimension system. On the same case, if we look at this one being, let's say, on the Cartesian plane, now the second system is on the along y-axis. That is also in one dimension. So what is the superposition principle is all about? According to the principles behind the superposition principle, it states that, let's say we have this system. Let's consider the mass M1. Each mass is exerting force on mass M1. What is the net force in which each mass is exerting on it? What is the net force in which each mass M1 as well as M3 is exerting on mass 2? What is the actual net force in which the two masses are exerting on M1? What is the net force in which M2, in which the other two masses are exerting on mass M2? That's the principle behind the superposition principle. So what is a superposition principle, as I have already put it forward? Now this principle states that when two or more effects act simultaneously on a system, the resultant effect is the sum of the individual effects, provided the system is linear. That's what we call as the superposition principle. You should have to understand. And we have a superposition principle in one dimension. That's when the system of the masses are in one dimension, as I have already shown you. And also be able to discuss about the superposition principle in two dimensions, as we are going to discuss in the same video. So let's start with superposition principle in one dimension. Let's say we have the system of the masses. Let's say this is mass 1, and let's say we have this is mass 2, and let's say we have this is mass 3. Let's say that is the case. And now we understand that each mass is exerting the force on on the another mass. That is according to the Isaac Newton, as we have already talked about it. And now let's think of having, let's say, the net force acting on, let's say, a mass M1. And now the expression will be given as F1 net. That corresponds to that corresponds to have the net force acting on mass 1 due to the other masses. So should be that, which is equal to, so we understand that we have it as F12 and also have it as F13. That is the force on 1 due to 2, force on 1 due to 3. That is. And in a simplest way, I can call this one being given as the parent, and this is the parent mass, and this is the daughter mass. Actually, this is the daughter mass. This is the parent mass, this is the daughter mass. That's how I can have it for the sake of simplicity in the analysis. Now, we should give the directions of the forces. And now, since the force is attraction, and in all cases, the direction of the force must be from the parental, actually, must be from the parent mass. Therefore, the force will be from the mass 1. But now, looking at the two masses, this is where mass 2 is found. And therefore, the force, which is F12, will be towards that direction. And since it is towards the positive direction, we'll have the force F12 being the positive. And by the way, the force is vector, so have it as the vector as that. And how about F13? Now, principle remains the same. By the way, this is F12. And how about F13? Strumor, the force will be emanated from the parent mass, which is mass 1, and it will be towards this because the force is attraction force. So have it as that. That is the force F13. And since it is going towards the positive, the force will be given as the positive here. So have it being positive here in that way. So that's how you start to understand about the expression for the net force on mass actually 1. How about the net force, let's say F2 net? That is the net force on mass 2. How should you have that on? Principle remains the same. Or have it as F21 and F23. But how should you tell the directions? Now for this case, the direction of the force will be emanated from the parent actually mass, which is a mass 2. And since it is attractive, you know it will be towards that direction. Hence, we'll have it as the negative. And this, the direction will be from mass 2 towards that will be the positive direction. Therefore, have it as the positive here. That's how you should have to understand that one. And how about, let's say, if we have F3 net? So how should you have the expression? So in this case, we'll have F31 as well as the F32. But how should we tell the directions? So from mass 1, it should be from mass 3. What is the direction of the force to mass 1? That will be towards the negative, or have it as negative here. Likewise, this one also be negative as well. You just have to get in that way. What if, let's say, we have this kind of a system? How should you have to tell that one? Let's say we have the same case here. Let's say that is the case, and it should be that. And let's say this is the mass 1, mass 2, mass 3, let's say mass 4. So how should you have, let's say, F3 net, if that is the case? What would be the expression? This is true more the system in one dimension, which you have to understand. And now have it as F31, F32, F34 in that way. But how should you tell the directions? We should have to decide in that way. So F31, the force will be from here towards that. That will be negative because it will be going towards the negative direction. And the F32 also have the negative, and this one will be given as the positive. And on your own, try to have what is F1 net and what is, let's say, F4 net. What if, let's say, F2 net in your own case in that way. So that's how you start to understand about the superposition principle in one dimension in the actually in that case. Let's say we have now the actual case. This is, let's say, 20 kgs. By the way, the masses has to be in kgs. And let's say this is 50 kgs. And let's say this is 5 kgs. And let's say this is should be given as 2 kgs. Let's say we have that understand. Let's say this is 2 meters. This is 1.5 meters. And let's say this is should be 1.2 meters. Let's say that is the case. So what is the net force? Let's say in the direction. When let's say we have this is the mass 1, mass 2, mass 3, let's say mass 4. What is the net force in the direction on, let's say, a mass 1? So first thing, we should have to come up with the expression that will be given as A for 1, 2, or have A for 1, 3, and I also have A for 1, 4 in that way. And I wish to come up with the signs corresponding to the directions. So for this case, we'll have it as F12. What is that? Will be positive. And F13 also be positive as well. This one also be positive as well. So we should have to calculate these forces using the Newton's law of the universal gravitation force. So let's start with F12. F12 be given as G mass 1 times mass 2 divided by the separation distance. How far apart are the two masses? So what is G? We have it as 6.7 times 10 to the power should be about negative 11, like that. So we should have it in that way. And I should have it as times. What is the mass 1? We have it as 20. And what is the mass 2? We have it as 15. But in your case, you just have to do this step by step. Don't rush. So that is given as 6.67 times 10 to the power negative 8. Divided by what is the distance? We have it as 2 to the power 2, that is given as 4. And by the way, we have it in newtons. And what would be that? So we have it as divided by 4. That will be given as 1.67 times 10 to the power negative 8 newtons. So that is the force F12. We'll have to keep it here. That is the force F12. I'll keep it here. That is 1.67 times 10 to the power negative 8 newtons. Let me have it there. And should also have what we call as F13. So what will be the F13? F13 using the same formula, we'll have it as G mass 1 times mass 3 divided by the separation distance. So what is the G? We'll have it as 6.67 and times 10 to the power negative 11, like that. By the way, you should have, so make sure you are having all these in brackets whenever you are plugging them on the calculator. So what is the mass 1? You have it as 20. And what is the mass 3? It's between mass 1 as well as the mass 3. That is 5. That should be given as 6.67 times 10 to the power negative 9 divided by what's the separation distance between the two actual masses? That is should be 3.5. And 3.5 to the power 2, that will be given as 12.25. And should be that. And now should be 6.67 times 10 by the way, 6.67 and times 10 to the power negative 9. You know that corresponds to divide by, let's say, 12.25. And this one is given as 5.44 times 10 to the power negative 10 newtons. That is F31. Should be F13 rather, or have it as that, which is 5.44 times 10 to the power negative 10 newtons. So let's have it in that way. And from there we should also have what is that of F14. So what would be that? So F14 corresponds to have it as F14, which is equal to the G mass 1 times mass 4 divided by the separation distance. And that should be given as 6.67 times 10 to the power negative 11 in times what is mass 1, that is 20, and what is mass 4, that is 2, should be given as 2, and that is given as, should be 2.67 times 10 to the power negative 9 divided by the way, we should have it in newtons, so be careful with the units there. So what's the separation distance? We have that one as, should be 2 plus, by the way, 3.5 plus 1.2, that is being given as 4.7, and square the separation distance. What would be that one? That should be given as 22.09, and should be that. Now 6 should be 2.67 times 10 to the power negative 11. What will be that? And basically divide by 22.09. That should be given as 1.21 times 10 to the power negative 10 newtons. That is F14. And from there we should have to combine the actual forces. We should have to combine the forces in the sense that we have it as F1 net being given as, what is that one? We have it as 1.67 times 10 to the power negative 8 newtons, and plus we have 5.44 times 10 to the power negative 10 newtons, and plus should be 1.21 times 10 to the power negative 10 newtons. That will be given as that, and from there we should now have it as, should be 1.67 times 10 to the power negative 8 in the plus 5.44 times 10 to the power, let's say, negative 10. That should be that. And also in the same case we have it as 1.21 times 10 to the power negative 10 as well. And what is that? We have it as 1.67 times 10 to the power negative 8 newtons. So this is the F1 net. And now from this point, now this is how you have to understand it. Now the magnitude of the force on mass 1 is given as this. Now the magnitude corresponds to have the F1 net without being given as a vector like that, and which is the same as this value. And the direction, since it is positive, will have to the positive direction. Had it been that it was a negative, then you could have said that the magnitude is given as the positive value itself, and the direction should be to the negative direction. So keep that in mind. Also in your own case, try to have the net force on this as well as this. So keep that in mind. So now let's consider this kind of a system. Let's say we have this archetypical system. Assuming that the net force, let's say the net force on 3 is given as 0. What is the position of, or should I say, what is the value of x? Given that should be a mass 3 is at equilibrium. So being at equilibrium, it means the net force is given as 0. What should be the value of the x in that way? So try to look over that one at your own time. And what if, let's say, we have this kind of a system, just this typical system. Let's say this is the mass m. Let's say that is the case. Let's say this is 6 grams, 10 grams, let's say 20 grams. So now assuming that the F, let's say 3 net, F3 net is given as our, let's say this is 2 meters, let's say 3 meters. Let's say that is the case. What is the value of the mass m1? And given that F3 net is given as our. So now let's say this is the system. Let's say this is mass 1, mass 2, mass 3, mass 4, and let's say this is the mass 5. And all the masses are in, let's say, the kgs. So what is F2 net of the system? By the way, this is should be 2-dimension system. And our first thing, we should have to come up with the expression that relates the forces on the system. But now, as we are coming up with the expression, we don't need to care much about the directions first. Firstly, we should have to literally add the forces. That will be given as F21, we'll have it as F23, and plus, let's say, F24, and plus, let's say, F25. We'll have it as that. And from there, that's when we should have to analyze the forces on the given system. Let's go on F21. Should be F21. F21 corresponds to the 2 masses here. So let's think of connecting the 2 masses. So this is how they are. And let's say this is 2 meters. Let's say this is, should have it as 3 meters. And let's say this is 4 meters. And let's say this is 5 meters in that way. So what is the separation distance between the two, actually, the masses? We don't know what is that. But much as we are looking for F21, it means the force will be emanated from the mass 2. Now for that case, this is where the force has to be. This is where the force has to be, like, that is the force F21. And from where the force has been emanated from, we should have to develop the 2-dimension Cartesian plane from that point. So we should have it as this. And these are the coordinates, I should say the components of the force F21. Let me have this. And this is the force F21. That has to go like that. And these are the components. We should have to come up with the 2-dimension Cartesian plane from where the force is coming from. So it should be that. That is the force F21 in that way. And we don't know what is the separation distance that our equators are. But using Pythagoras theorem, this is Lagrange triangle, that one, we can be able to have what is that R. So let's think of having the separation distance using the Pythagoras theorem. So R, which is the hypotenuse, will be given as 2 square plus 3 square. That is the same as we have it as 4 plus 9 r square. What is that? Which is given as it should be 13. And therefore, we'll have the r square should be r being given as the square root of 13. So what is that? And which is given as 3.6. Should be 3.61 meter. That is the separation distance r. So you need to show all these works we're having it here. Let's say during the exams, in case you are having such kind of a case, you should have to show whatever you're doing. Then from there, we should be able to have what is the force F21 using the formula. That is given as, that should be given as the G M1 times M2 divided by the separation distance square. And by the way, R is given as 3.61 meter. We should have that. So what is the G? We have it as 6.67 n times 10 to the power negative 11. In times, what is the mass 1? That is 2. And what is the mass 2? We have it as 5. And from there, we should have to divide the separation distance square. That is been given as F12, which is given as 5.12 times 10 to the power negative 11 newtons. Let me keep it here. That is F12, which is given as 5.12 times 10 to the power negative 11 newtons. So have it as that. And from there, we should also have to think of resolving the force into components. So we should have to resolve this force into components. Whereas this is the x component, that is F2x, and this is y component, that is F2y. We should have to resolve that into components. That you should have to understand it in that way. So how should you have it? You know, first of all, we should have, let's think of having this angle. We should have that angle. That is the opposite adjacent. Or else you may think of having this angle instead of this angle. That is the same. So if you are to use this angle, it means this force is against the vertical, which is the y-axis. If you are to use this angle, it means the force is against, should be the force is against the x-axis. At the end of the day, this angle is the same as this angle, the reason being the orient angles. So if we have this angle, will be the same as this angle, then the force will be resolved from the fact that the force is against the x-axis. So it should be that. So let's think of resolving, let's think of having this angle, that will be the same as this angle. So let me have this. That is the angle theta, which is the same as this. So we should have to calculate this angle. What is that? Using the trigonometric ratios, tan adjacent. That is the same as the tan theta. And being the same as, what is the opposite? That should be 3 divided by, what is the adjacent? That is given as 2. And therefore, we'll have the tan inverse. So it should be the tan inverse of, it should be 3 divided by 2. You know, which is the same as theta being given as 56.31 degrees. That is the angle theta. And from there, we should have to resolve the force into components. And mind you, you should have to understand about the vector resolution. Whatever I'm doing here, it's about the vector resolution. But now we have f12x, which is equal to, now it is going towards the negative direction. We'll have it as the negative f12 cos theta. By the way, this angle is the same as this angle. So therefore, we are resolving with respect to this angle theta, as I already put it forward. And now since it is going towards the left, we'll have it as the negative. So in that way. So in this case, what we have is what is a f12? We have it as 5.12 times 10 to the power negative 11 sort of, and that times what is we have it as the cos of 56.31. That is now been given as 2.8, should be 2.8, and that times 10 to the power negative 11 newtons. That is the x component. That is a negative 11 newtons. That is the x component, and I'll have it as I in terms of the unit vector. And how about the f12y? And since it is going downwards, that should be given as the negative as well. That will be given as the negative f12 sin theta. We'll have it as the negative. And what is that? We'll have it as the, by the way, we should have it negative here. And that is, we should have it as 5.12 times 10 to the power should be negative 11 in times sine of 56.31. That is now been given as should be 4.26 times 10 to the power negative 11 newtons. And since this is y, I'll have it as j. So keep that in mind. So the components are given as, let me have it here. The x component, now have it as f12 as a vector, now is given as, so should be the x, which is given as the negative 2.8 and times 10 to the power negative 11. And by the way, let me keep this aside. I'll come back with him later. So that's we are done with the first force. Let me create the space and have the another analysis on the other cases. So as you can see, whatever we're doing here, nothing new. We're just using the concept of the vectors. You should have to understand how the vectors are being resolved for you to have for this in right way. And now we are done with the force F21. We should have to go on the force F23. And what is that? So that is now between the mass 2 should be, by the way, it should be between the mass 2 as well as the mass 3. And on the same case, we should have to connect the two actual masses like this. So we should have to connect the two masses like that. And the force has to be from, should be mass 2 like the same way. And therefore, I'll have it as this. And that is the force F23 like that. And from where the actually a force is being emanated from, you just have to come up with a two-dimension, Cartesian plane. That is, let me use another key. And for the beta visualization of this. And now for this case, what you can have is, this is the force F23. And now we should come up with, we should have to develop the two-dimension coordinate system. It should be actually a coordinate system there. And this is the force, and these are its components. That is, we have it as F. That is F23x, and that is, indeed, we have this one as the y component, which is pointing downwards. And now we should have the separation distance. What is the separation distance? Using the same principle, we'll have to use the Pythagoras theorem. Since this is the right angle triangle, we should have the separation distance, which is given as r. What is that? R square is given as, we have 9 plus 16. So should be 9 plus 16. What is 9 plus 16? 9 plus 16, which is given as 25. So half to 25. What is the square root of 25? That is the same as 5. Therefore, the separation distance is given as 5 meters. So R corresponds to half as 5 meters. And using the universal gravitation law, have it as what is F23? It is now been given as the G m2 times mass 3 divided by the separation distance square. That is given as 6.67 and times 10 to the power negative 11 and times what is mass 2, that is 5, and times what is mass 3, we have it as 10, and which is that, and that divide by the separation distance square, that is 25 as well. That is 25. The which is given as should be 1.32, should be 1.33 rather. Let me have that on times 10 to the power negative 10 newtons. That is the force F23. And from there we should have to resolve the force into components. But how should you have to resolve the force into components? Let me put it here. That is the force F23, which is equal to 1.3 times 10 to the power negative 10 newtons. And now we should have to calculate this angle theta, which is the same as this angle. That's the ordinate angles. So how should you have this? Using the trigonometric ratios, that is the tan adjacent should be opposite adjacent, or else you can use this angle. That is the same as well. So let's use this angle to have that on. Now we have the tan inverse. We should have it as the tan inverse of, so should be the tan inverse of what is the opposite. We have it as 3 and divided by the adjacent, and which is the same as 36. So the angle theta is given as 36.9 degrees. That is the angle theta in that way. And from there we should have to resolve the force into components. Now that will have it as F for 3x, and since it is going to the right, we'll have it as the positive F23x, which is equal to F23 cos theta, and that corresponds to have it as, that is the I, because that is the positive, that is the x component, or have it as I. And what is that? F2 is given as 1.3 times 10 to the power negative 10, and it should be that. And now times the cos of, should be times cos of 36.9. That will be given as 1.0 times 10 to the power negative 10 newtons. Should be that. And what is the x? Should be the, what is the y component? F23y is given as, that will be given as F2, should be F32 rather, should be F23, should be F43. What is that? F23 and sine theta. What is that? And since it is going downwards, that is the negative. We'll have it as a negative. We'll have to assign negative there. And that is 1.3 times 10 to the power, should be the negative 10. So it should be, so that is to the power negative 10. That has to be given as times the sine of, what is that, times the sine of 36.9. And that is the same as negative 7.8 times 10 to the power negative 11 newtons. that is the J. And now I'll keep them somewhere, I'll come back to them later. And now that we are done with F23. And let's go on what we get as F24. What would be that? By the way, we should have F25 here. We should have that. So what is the F24? That corresponds to be between that of a mass 2 as well as the mass 4. And the direction of the force has to be from the mass 2 to mass 4. We should have it as this. This is how the force has to be. And what is the separation distance? That should be given as, we have it as 3. Therefore, we just have to go straight and have what is F24 in that case. So have it as the G M2 times M4 divided by the separation distance square. And what is that? We have it as 6.67 and times 10 to the power negative 11 and times what is mass 2, that is 5, and what is mass C, actually 4, that is 6. And that one divided by the separation distance square, that is should be given as 9. So just have that understand. And therefore the force is given as 2.2 times 10 to the power negative 10 newtons. That is the force F24. And how should you have to resolve that one? So F24x is equal to 0 because the force is along y-axis. And what is F24? Y will be given as the negative because it is going downwards, but it will be the same. So I'll take it out, I'll bring it later. And from there now I should have F25. So what is that? It is the connection between mass 2 as well as the mass 5, which is given as this, and the force has to be from mass 2. That is given as that. And what is the separation distance? We have it as 8. Now for that case, we just have to go straight and have what is F25. That is given as the G mass 2 times mass 5 divided by the separation distance square. And what is that one? We have it as G being given as 6.67 times 10 to the power negative 12. We should have that times what is mass 2, we have it as 5. And what is mass 5, we have it as 3. And then divide by the separation distance square, which is 64. And which means we have it as 1.56 times 10 to the power negative 11 newtons. Should be that. Then if we think of resolving into components, we'll have F25x being given as 0 because the force is around y-axis. And F25y will have it as the negative 1.56 times 10 to the power negative 11 newtons. So have it as that. So on the same case, let me take it away. And now we have managed to obtain the force F21, F23, F24 as well as the F25. Now we should have to combine the forces. And by the way, if you may wish, you can also have the net force on, let's say, mass 3, let's say the net force on mass 5, net force on mass 1, as well as the, let's say, mass C, it should be 4. You can also have it in the same way. But anyway, I'll take it out. So for this case, what it does is that we should now have to substitute into the expression. We have now F2 net. That is not being given us. I have to substitute these forces with their corresponding components. So that is for the case of F2, we have them as negative 2.8 times 10 to the power negative 11 newtons. That is I. And a plus 4.26 times 10 to the power negative newtons. That is around J. I should have that understood in the plus On the case of F23, we have it as the positive, that is 1.0 times 10 to the power negative 10 neurons, that is along X, and the minus 7.8 times 10 to the power negative 11 neurons, that is along Y, and the plus. On the case of F24, we have it as 0 neurons along I, the minus 2.2 times 10 to the power negative 10 neurons along J. And that one, on the case of F25, we have it as 0 neurons along I minus 1.56 times 10 to the power negative 11 neurons J. That's how we should have it. And from there, we should have to combine all actually X components. That is now been given as F2 net. We'll have it as, what are the summation of the X components? That is negative 2.8. That should be times 10 to the power negative 11. We just have to add this. And now if we combine actually X components, that will be given as the positive 2, should be positive 7.2 times 10 to the power negative 11 neurons, that is along X. And how about the Y components? And now if we combine the Y components, what it does is that we'll have it as 2.71 times 10 to the power negative 10 neurons. Should be about this. Should be neurons along actually X. Now sometimes actually the question can come. We should have to present the net force, let's say, on mass 2 in form of the unit vector notation. If that is the case, it means you are to stop here. That is, if you are told to have it in form of unit vector notation, or have it as that. But now we are looking for the magnitude as well as the direction. So what is the magnitude of the force? That is the net force, or the magnitude, which is the same as the square of that one plus that one. So that's the square. That's the square of x square plus y square. We'll have it as that. So what is the square of this? And now that corresponds to have it as 5.1 times 10 should be 1, actually 5.2 rather. We'll have it as 5.2 times 10 to the power negative 21 and plus, how about the square of this one? And now the square of that will be given as, and that should be given as 7.3 times 10 to the power negative 20. So have it as that. Then we should have the summation of those. So how should they have their sum? We can have it as, if we have the summation of those, what we'll have is, we'll have the F2 net being given as the square of, so have it the square of 7.8 should be 9 times 10 to the power should be negative 20. In that way we'll have it in neurons. And what is the square of that one? That will be given as 2.8 times 10 to the power negative 10 neurons. So this is the magnitude or the net force acting on the actual charge 2, I should say on the mass 2 due to the other masses. You should have it as that. And what is the direction? We'll have it as theta, which is the tan inverse of, which would be the tan inverse of this divided by that. And what will be given as that? So tan inverse of negative 2.71 times 10 to the power negative 10, that divided by 7.2 times 10 to the power negative 11. That will be given as, what is that one? We should have the tan inverse of, and that should be negative 2.71 times 10 to the power negative 10. And that's divided by 2.7 times 10 to the power negative 11. We should have it as that. And now the angle is given as negative 75.1 degrees. So this is the direction. So that's how you start to understand about the principles behind the actually universal law of the gravitation force according to this Isaac Newton. So that's how you should have it. Thank you.